Hello, students. Um, this is a representation here of a model of an atom, or it is a model of an atom. A model and a representation being very similar things. So, what we want to show here are that there are two main processes that happen um, that involve some of the things that we've seen experimentally, and particularly the things that were seen in the very early 20th century when when Niels Bohr specifically started this model of the atom. And what Niels Bohr saw when he looked at an excited sample of gas is that it gave off light of only very specific colors and only very specific frequencies. All right, and the photoelectric effect says that frequency and energy are are directly related. Now, the photoelectric effect sort of introduced the idea of photons, all right, and that light doesn't always behave like a wave; it behaves like little bundles of energy called photons. And so, light can act like these little packets. And when Niels Bohr saw that hydrogen gas, for example, only kicked out very certain colors, he said, there must only be certain energies that are released from an atom. So from there he developed the idea that electrons can only be in very specific orbits. Or we say that orbital radii / energies are quantized. There can only be specific allowable values of. That's what quantized means. There are only specific allowable values of. You'll remember this from electrostatics, that there are only specific allowable values of charge that are possible. So charge is a quantized quantity. All right? You can have an amount of charge only equal to an integer number of electron charges or elementary charges. All right, this is a little bit different than that, but Bohr said that electron energies or orbital energies and radii have to be only certain allowable values. And this is a representation of those values. Now, nucleus is in here. Like super, super, super small. So small you can't really see it. Right? We call this the n equals 1 state, or energy level, or ground state. This we call the n equals 2 state, or the first excited state. Here's the n equals 3. Here's the n equals 4. And the evidence that we see for this, well, is again these only certain bright colored lines that come out of, or that we see in what's called an emission spectrum. All right, the emission spectrum for hydrogen, the visible spectrum, has very specific bright lines. A red one, a turquoise one, a bluish one, and a purple one, and a more purple one. All right? And those things can happen, well, you see those things when an atom emits light. And so when an atom emits light, that happens because an electron can go from a higher energy to a lower energy. Right? This state has an energy that we'll call E4. This state has an energy we'll call E3. All right? And when this happens, when an electron, what we call decays into a lower energy, well, that energy is released in the form of a photon of a certain energy. Well, and that energy, or the photon, is the difference in the two energies of the orbital it started at and ended it. Okay? Now, that electron could also, maybe, instead of dropping to n equals 3, drop all the way to n equals 2. And if it did that, well, this would emit a photon of more energy, right? This photon would have an energy of E4 minus E2. More energy, higher frequency. So I could draw that, almost like that. Shorter wavelength, higher frequency. There's E photon equals E4 minus E2. Just going to move this. N here, so we're sure, is not index of refraction at all. Just an integer, the quantum number, the state number. That's what we call it. Okay, so how do atoms emit photons? Well, electrons move from higher energy states that I'll say larger radii to smaller ones, or smaller radii. So from higher energy to lower energy, higher radius to smaller radius. Okay? And when do atoms absorb photons? Well, if and only if they're able to absorb energy. And that can happen if we have just the right amount of energy. Let's just say we have an electron in the ground state. Well, if we want to make it excite, if we want to excite that electron up to the n equals 3 state, that means we must have to kick in a photon that is, here's the big deal, exactly equal to the difference in the two energies. I'm going to do this, absolute value. There's signs, stuff that I wouldn't worry too much about. Just look at the difference, just look at the absolute value of the difference, right? Or the difference of the absolute value, or something like that. Okay? So we absorb a photon. So if and only if, sometimes I do IFF, if and only if a photon has exactly the energy equal to the difference between two states. Or, there's one other sort of case that you'll recognize. Okay? So we can either absorb a photon and excite an electron, or an electron can decay and emit a photon. Now, the electron doesn't emit the photon, the atom does. Right? The electron doesn't absorb a photon, the atom does. So there's a lot of things to keep straight here in terms of terminology. Right? The atom absorbs or emits a photon. Right? The photon is absorbed or emitted. Right? The electron can be excited or decays. All right, so just make sure we're doing our best to, use the right terminology of what's happening to what thing. The atom we're talking about, is it a photon, is it an electron? Okay, and those can be tricky to keep straight. Okay? Now, here is a diagram called an energy level diagram that shows the energy states of various, the energies in EVs, in electron volts, of various states in a hydrogen atom. Various orbital energies for electrons. All right, and if you remember, there's a potential energy, electric potential energy, goes like that, right? And these two charges, electron, and for hydrogen, proton. So that's why these energies are negative. It's part of the reason. All right, because electron, negative charge, Proton in the nucleus, positive charge. Right? So these energies, the potential energies, can be negative. And remember also, the bigger R gets, the bigger the separation between the two, the smaller the energy. All right? The bigger R gets, the smaller the energy. But it's negative. So that's why this graph actually looks like that. The biggest energy you could possibly have, what we want is, if we bring an electron farther away from the proton, from the nucleus, we want it to have more energy. But what's the most energy it could ever have? The farthest away things ever get, the energy gets to 0. So that's why we want this function to work like it does. That's a little bit more info than we need. But here's that energy level diagram. Right? And if we look at a few transitions, or a few states, let's just choose arbitrarily, let's look at electrons that either transfer from or to the n equals 6 energy state, or n equals 6 orbit. Now, from n equals 6, the electron could go to any of these other states. It could go to 5. Anybody?
Sorry about that.
Sorry. So this electron could transition from 6 to 5, from 6 to 4, from 6 to 2, or it could go from 3 to 6, or from 4 to 6, or from 1 to 6. All right? And so the important thing for us to look at is the energy of a photon, which is really this part, E photon, which is equal to the difference in the energies of those two states. All right, so if you look and compare energy of state 6, energy of state 5, the difference is 0.16 EVs. From 6 to 4, the difference is 0.47 EVs, right? 6 to 4. 6 to 3, the difference is 1.13. And so on and so on. Okay, using E equals HF, we can find the photon frequency. I'm not showing the work, but I trust you can follow. All right, now the color, this part, what we have to do, what I have to give you is, we have to look at the electromagnetic spectrum. So we'll pick a copy of that up tomorrow, and I'll show you a place where we can figure out what color these photons are. Only one of them is visible. Okay? You okay here? Fair enough so far? All right. Now, a couple of real important things. One is, let's say we have a electron in the n equals 2 state, right? Well, the energy of state 2 is negative 3.40 EVs. Okay? So what would a 1.94 EV photon do to that? Well, it would change the energy up to, let's see, so 3.40, really negative 3.40 plus 1.94 gives us negative 1.46 EVs. So what we do is say, is there an energy state of 1.46 EVs? Well, there isn't. There's nothing in between 0.85 and 1.51, right? The energies can't be anything of these states. They have to be only very specific allowable quantities, and those quantities are the ones that you see here. So since there's no 1.46, nothing happens. So really what we're saying is this photon is not absorbed. And that electron just sits there like nothing ever happened. All right, now notice there is this 1.51 state, and it says, well, couldn't we just take some of the energy and just leave a little bit, take some of the energy out of that photon and be left with some more, and make the transition to here and be left with a few extra, hundredths of an eV. Well, that doesn't happen. You can't take that photon and break it up. Okay, so I'll say to get to state n equals 3, E photon has to be equal to exactly the difference in those two states, right? That's 1.89 or something. Yeah, I think it's 1.89. So E photon has to be exactly 1.89 EVs, no more, no less. Here's the kind of however, or the exception to that. In the n equals 3 state, here's an electron. Now, energy of that third state, like we showed, is negative 1.51 EVs. Well, if we throw in that same 1.94 EV photon, that's actually enough to get this energy all the way to 0. So if we plus 1.94 EV, we get negative 1.51 plus 1.94. Well, we get 0.43 EV. And that means that that's enough energy to get this electron from here, well, all the way to this n equals infinite state, where it has 0 energy, or it's enough to ionize the atom. So this is 1.94 EVs is enough to ionize the atom. Remove the electron. And what happens to this? Well, I'll say, and give it 0.43 EVs of kinetic energy. So we're sort of back to this idea of photoelectric effect. Right? We're not saying hydrogen's a metal, but what we can do is shoot photons at a substance, and if we shoot photons of enough energy, what we can do is kick electrons completely out of the substance and have some kinetic energy that they're left with. Okay? So typically, in many cases, it's real important that energies of photons are exactly the difference between two energy states. Unless, like over here, when that energy is enough to completely remove the electron from the atom. And in that case, any excess energy goes to being kinetic energy of the electron. Fair enough? Yeah. Okay, folks? I think that's it for now. See you soon.